Please subscribe to support the channel. The idea that Earth is a pinnacle of habitability is being overturned by a new and exciting frontier in astronomy, the discovery that some distant worlds, so-called superhabitable planets, might actually offer environments even more nurturing and life-friendly than our own. Scientists now suspect that Earth, as vibrant as it is, may not be the universe's best example of a life-bearing world. After all, our planet has endured violent climate swings, mass extinctions, asteroid strikes, and long stretches of inhospitable conditions. Meanwhile, beyond our solar system, there may exist planets with more stable climates, thicker and more protective atmospheres, longer-lasting oceans, warmer average temperatures, and host stars that shine steadily for tens of billions of years, especially orange K-type stars, offering life far more time to emerge and evolve without the threat of early stellar death or extreme variability. This emerging realization challenges the traditional search for Earth 2.0, suggesting instead that the most promising world for abundant, thriving life might not resemble Earth exactly, but surpass it, offering richer biodiversity, deeper evolutionary histories, and environmental stability on a scale our planet has never known. The concept of superhabitability reframes humanity's cosmic expectations, proposing that the universe may harbor worlds where life not only survives, but flourishes far beyond Earth's limitations, giving us new hope in the search for alien ecosystems and perhaps even a better home for our distant descendants. When scientists use the term superhabitable, they are describing planets that, based on theoretical models and observational data, could offer conditions even more favorable for life than those on Earth, not merely capable of sustaining life, but actively enhancing it. The concept emerged from recognizing that Earth's habitability sits within a narrow range of possibilities, and that many of its qualities are not optimal, but simply adequate. A superhabitable planet, by contrast, would exist in a sweet spot of environmental balance, warm but not scorching, stable but not stagnant, and rich in resources that help biological systems flourish on a scale potentially greater than what we see here. In this view, habitability is not a yes or no category, but a spectrum, and Earth occupies just one point along it, far from guaranteed to be the most favorable. A superhabitable world would likely be slightly larger than Earth, providing more surface area for ecosystems to thrive, and a stronger gravitational pull to hold on to a thicker, more protective atmosphere. Its climate would lean warmer, because higher global temperatures tend to support greater biodiversity and more robust plant growth, as seen in Earth's own tropical regions. Liquid water will be plentiful, but instead of being locked in deep, nutrient-poor oceans, much of it would exist in shallow seas and lakes, where sunlight easily penetrates, fueling photosynthesis and complex ecological networks. These planets would orbit stars that shine steadily for tens of billions of years, especially orange K-type stars, offering life far more time to emerge and evolve without the threat of early stellar death or extreme variability. Scientists also imagine superhabitable planets as geologically active because plate tectonics help recycle nutrients, regulate atmospheric gases, and maintain long-term climate stability. Too much geological violence can sterilize a world, but too little leaves its ecosystem starved over time. Superhabitability lies in that balanced middle. The terrain would be varied, offering coastlines, islands, mountains, and plains that stimulate evolutionary diversity the same way Earth's most productive regions do. Even the planet's age matters. Worlds slightly older than Earth would have had more uninterrupted time for life to diversify, potentially hosting biospheres unimaginably ancient and complex. All of these traits, size, warmth, water distribution, geology, star type, and age, combine into a framework that researchers use to define superhabitability. It is a way of acknowledging that nature is not limited to Earth's template, and that the universe may contain planets that outperform our own in every category that influences the emergence, stability, and richness of life. Instead of searching for Earth replicas, astronomers are now widening the search to find these cosmic overachievers, world where life doesn't just survive, but thrives in ways we have yet to witness. And realizing this opens the door to the next question. If such planets may be superior in their capacity to support life, what exactly makes Earth fall short of the optimal conditions we once assumed it had? Although Earth is often celebrated as the perfect cradle for life, a closer look at its history reveals a world that has survived more by resilience than by ideal conditions. Our planet has endured catastrophic asteroid impacts, supervolcanic eruptions, dramatic ice ages, and abrupt climate swings that nearly extinguished life multiple times. These chaotic events weren't just occasional. They shaped Earth's evolution, creating long stretches where life struggled to survive rather than flourish. From the mass extinction that wiped out the dinosaurs to periods when nearly all complex organisms perished, Earth's story is punctuated by instability, making it clear that while the planet sustains life, it isn't consistently gentle or nurturing. In fact, some scientists argue that Earth's evolutionary timeline is unusually turbulent, and that many aspects of the planet's environment have actively hindered biological progress rather than encouraging it. Even Earth's sun, the Sun, is far from the ideal host for long-term habitability. While stable on human timescales, the Sun is a middle-aged G-type star that will grow hotter and brighter over time, eventually rendering Earth uninhabitable long before it reaches its natural end. Most estimates suggest that Earth will lose its ability to support complex life within just 1 to 2 billion more years, as the Sun increases in luminosity, boiling away the oceans and destabilizing the climate. In cosmic terms, that's a relatively short window. By comparison, smaller and cooler stars, especially K-type stars, can remain calm and life-friendly for up to tens of billions of years, providing far more time for life to arise and adapt, diversify, and potentially become intelligent. Earth's host star, impressive as it may be, doesn't offer that kind of long-term reliability. Moreover, Earth's geography and climate distribution are not optimal for maximizing biodiversity. Much of the planet's surface is covered by deep, nutrient-poor oceans that limit the variety of ecosystems they can support. The continents themselves shift unpredictably through plate tectonics, and while this process is essential for recycling carbon and regulating climate, it also causes destructive earthquakes and volcanic eruptions that reset ecological progress. The planet's axial tilt and orbital variations contribute to ice ages and warm periods that can dramatically reshape habitats, forcing species into cycles of expansion and collapse. In the grand scheme, Earth is better described as precariously habitable rather than perfectly suited for life. Even Earth's atmosphere has its shortcomings. While protective, it is vulnerable to fluctuations in greenhouse gases, which have repeatedly driven the planet into extremes, sometimes scorching hot, sometimes globally frozen. The balance of gases that supports life today is the result of countless biological and geological feedback loops that could easily have tipped in different directions. A slightly weaker magnetic field, a few more volcanic eruptions, or a slightly dimmer sun at certain points in history could have derailed life entirely. Our world is not a carefully tuned paradise. It is a planet that has walked a razor's edge for billions of years. Understanding Earth's limitations is vital because it reveals a broader truth. Habitability is not about achieving a single perfect set of conditions, but about how stable and forgiving a world is over enormous spans of time. Earth has been generous in its own way, but it is also filled with hazards, instabilities, and cosmic deadlines. When scientists contrast Earth with the characteristics of superhabitable planets, they find that many potential worlds could avoid the pitfalls that make our own planet so precarious. And this naturally leads into exploring the key scientific criteria that researchers use to determine whether a distant world might surpass Earth in its ability to sustain and nurture life. When scientists evaluate whether a planet could be superhabitable, they rely on several major scientific criteria that together paint a picture of a world's long-term suitability for life. One of the first factors they consider is planetary mass, because mass influences almost every other trait a world possesses. A planet slightly larger and more massive than Earth, about 1.2 to 1.5 times our planet's mass, is believed to be ideal. With more mass comes stronger gravity, which helps a planet hold on to a thick, stable atmosphere over billions of years, protecting life from harmful radiation and reducing the risk of atmospheric escape. Stronger gravity also supports more robust geological activity, which can promote nutrient recycling and climate regulation. Yet, it must not be too massive. Planets much larger than Earth may form crushing atmospheres or become mini Neptunes, smothering life under extreme pressure or burying the surface beneath thick gas layers. Superhabitability sits in a balance where gravity enhances stability without overwhelming biology. Temperature is another crucial criterion, and here the data points toward worlds that are slightly warmer than Earth on average. Higher temperatures generally increase biodiversity, allowing ecosystems to flourish across wider regions. Warm conditions create larger tropical and subtropical zones, regions where life tends to thrive most intensely due to abundant sunlight and rapid biological turnover. But warmth must be evenly distributed. Planets with uniform climates and minimal temperature extremes are better suited for maintaining stable ecosystems. Scientists believe that worlds with mild seasons and minimal glacial cycles offer far more consistent opportunities for life to diversify than planets that oscillate between ice ages and warm periods as Earth has done repeatedly. A superhabitable planet would likely maintain surface temperatures in a comfortable, stable range for billions of years without catastrophic climate swings. Age also plays a fundamental role in determining superhabitability. Older planets, those that formed earlier in their star's history and have remained geologically active for longer, offer more time for life to arise, adapt, and evolve complexity. Earth is around 4.5 billion years old, and complex life emerged relatively late, only around 600 million years ago. A planet that is moderately older than Earth, perhaps 5 to 8 billion years old, could potentially harbor ecosystems that had a far longer, uninterrupted timeline to diversify. However, age also comes with caveats. The planet must not have cooled too much, lost its geological activity, or suffered atmospheric erosion. The most promising worlds are those old enough for life to have fully explored evolutionary possibilities, yet young enough to retain a nurturing environment. This delicate balance makes age a powerful indicator in habitability studies. Atmospheric stability may be the most important factor of all. A stable atmosphere regulates temperature, shields life from solar radiation, and maintains the delicate balance of gases necessary for biology. On Earth, this balance has been achieved through a mix of biology and geology, but it has also been highly fragile. For instance, a slight change in greenhouse gases has historically plunged Earth into ice ages or warmed it to near uninhabitable levels. Superhabitable planets are expected to have atmospheres that remain stable for billions of years, with slow rates of change and resilience against stellar flares, volcanic events, and orbital variations. A thicker atmosphere also supports efficient heat distribution, preventing extreme hot and cold regions and creating a more uniform climate overall. This stability is crucial for supporting rich ecosystems that do not face constant environmental disruptions. Taken together, these criteria, mass, temperature, age, and atmospheric stability, form the backbone of the scientific search for superhabitable worlds. They provide clear, measurable indicators that help researchers determine whether a distant exoplanet might not just resemble Earth, but surpass it in its ability to support abundant and enduring life. And once these planetary traits are evaluated, scientists look outward even further to the stars themselves, because the type of star a planet orbits can dramatically enhance or limit its potential for superhabitability. The type of star a planet orbits is one of the most influential factors in determining whether that world can become superhabitable, because a star shapes everything from climate to atmospheric chemistry and long-term habitability. While our Sun has provided Earth with enough stability to sustain life for billions of years, it is far from the ideal stellar host. G-type stars, like the Sun, are relatively short-lived on cosmic timescales and tend to grow hotter and brighter as they age, gradually shifting their habitable zones outward. This means Earth is living on borrowed time. Within a billion or so years, increasing solar luminosity will disrupt our climate, evaporate our oceans, and eventually render the planet uninhabitable. In contrast, planets orbiting long-lived, quiet stars, especially K-type stars, exist in a far more forgiving and stable environment that can support life for much longer periods of time. K-type stars, often called orange dwarfs, occupy a sweet spot between the hotter and more unstable G-type stars and the unpredictable flare-prone M dwarfs. They burn cooler and more efficiently than the sun, allowing them to shine steadily for 20 to 70 billion years, several times longer than our star's entire lifespan. This extended stability gives planets in their habitable zones immense stretches of time to develop life, weather planetary changes, and allow evolution to advance without the pressure of an impending stellar expiration. Not only do K-type stars live longer, but they also exhibit fewer disruptive flares and radiation spikes compared to M-type red dwarfs, which frequently bombard nearby planets with harmful radiation. The calm nature of K-type stars means any nearby world is less likely to lose its atmosphere or face sterilizing events that could reset or destroy emerging biospheres. Another advantage of these stars lies in the width and stability of their habitable zones, the region where temperatures allow liquid water to exist on a planet's surface. Because K-type stars remain stable for so long, their habitable zones shift very slowly compared to those around brighter, faster evolving stars like the Sun. A planet sitting in this stable zone could remain in the right temperature range for tens of billions of years, giving life a continuity that Earth has never experienced. This slow, predictable evolution of the star and its output minimizes catastrophic climate disruptions and expands the evolutionary potential for life. The result is a cosmic environment that encourages biological endurance and complexity. Even the energy output of K-type stars contributes to superhabitability. Their light spectrum is gentle, less ultraviolet radiation than the sun produces, which helps reduce atmospheric erosion and protects surface life from harmful radiation. This softer radiation profile also encourages the retention of thick atmospheres, which are crucial for maintaining climate stability and protecting organisms. Combined with a moderate temperature range, these stars create conditions where liquid water can remain stable across broader areas of the planet's surface, increasing the availability of habitable environments. When scientists search for the most promising superhabitable worlds, planets orbiting K-type stars rise to the top of the list. They offer unmatched longevity, reduced volatility, and stellar environments that allow life to take slow, steady steps toward complexity. This makes them not just good candidates, but potentially the best hosts for rich, sustained biospheres. And with this understanding of stellar influence, researchers turn their eyes toward real exoplanetary systems, worlds already identified as potential superhabitable candidates that might surpass Earth in the very traits that define habitability. As astronomers expand their search for worlds beyond our solar system, a growing list of exoplanets has emerged as promising candidates for superhabitability. Worlds that, based on current data, may possess traits more favorable to life than Earth's. This catalog is still evolving, informed by both observational discoveries and theoretical models, but several planets have consistently stood out in scientific literature. Among the most discussed are exoplanets like Kepler 442b, Kepler 452b, Kepler 62e, Kepler 62f, and particularly Kepler 1229b and Teegarden Star b, each offering combinations of size, temperature, stellar environment, and potential atmospheric conditions that place them within or even above the expected thresholds of habitability. While not all of these planets are confirmed to be rocky or Earth-like in composition, the available data suggests they may possess stable climates, long-term stellar support, and environmental factors that could sustain rich ecosystems. These worlds are part of a broader set of exoplanets selected from thousands discovered by missions like Kepler, TESS, and surveys using ground-based observatories. One of the foundational works in identifying superhabitable candidates was conducted by Renee Heller and John Armstrong, who proposed a short list of worlds that most closely match the criteria for superhabitability. Many of these worlds orbit K-type stars, the quiet, long-lived suns that offer exceptional stability for planetary biology. Worlds such as Kepler 442b, which orbits an orange dwarf star and sits comfortably within its habitable zone, have drawn particular interest because they combine an Earth-like size with a potentially more forgiving stellar environment. Kepler 62e and Kepler 62f, two planets in a system about 1,200 light-years away, remain compelling because their sizes and orbital positions suggest climates where shallow oceans and stable temperatures might be possible. Researchers continue to refine their assessments using newer data models that evaluate mass, atmospheric retention, and potential surface temperatures. Other candidates, such as Kepler 1229b, gain attention because they orbit stars that are old and calm, providing an environment that may have remained stable for billions of years, ample time for life to evolve complexity. Meanwhile, Teegarden star B, though orbiting a smaller M dwarf, is close enough and well-studied enough that scientists have begun modeling its surface conditions with greater confidence. It remains a candidate because it lies near the middle of its habitable zone and may have retained its atmosphere due to the star's surprisingly low activity level compared to typical red dwarfs. As technology improves, additional planets are being added to potential lists, especially those discovered by TESS, which continues to identify rocky worlds around bright, nearby stars, the very systems where future telescopes will be able to study atmospheres directly. The catalog of superhabitable candidates is still in its infancy, but it represents the first generation of worlds that might rival or surpass Earth in their capacity to support life. These planets serve as stepping stones, guiding astronomers toward the most promising targets for future atmospheric studies, biosignature searches, and eventually, perhaps one day, interstellar exploration. And within this growing list, a few exceptional worlds rise above the rest. Exoplanets whose features make them the most compelling and potentially the most life-friendly environment we have ever identified. Among the growing catalog of potential superhabitable planets, a handful stand out as especially compelling, worlds that consistently rise to the top in discussions because they combine multiple favorable traits, from ideal temperatures and sizes to long-lived, quiet host stars. One of the most frequently highlighted examples is Kepler 442b, a rocky exoplanet located about 1,200 light-years away. Kepler 442b is roughly 1.3 times the size of Earth and orbits an orange K-type star that provides steady, moderate stellar radiation. What makes this planet truly compelling is that climate models suggest it receives just the right amount of energy to maintain stable liquid water conditions over vast spans of time. Its star's long lifespan means the planet has likely been within its habitable zone for billions of years and will remain there for billions more, granting life an expansive evolutionary runway. Although we have not yet confirmed its atmosphere, the combination of size, stellar type, and orbital distance makes Kepler 442b one of the strongest superhabitable candidates currently known. Another standout world is Kepler 62e, located in a system with two potentially habitable planets. Kepler 62e is particularly intriguing because it appears to be slightly larger than Earth, about 1.6 times in radius, and sits in the inner region of its star's habitable zone. This position suggests a warm environment where shallow oceans might dominate the surface, potentially creating vast stretches of nutrient-rich waters ideal for fostering diverse marine ecosystems. Its star, another long-lived K-type dwarf, offers immense stability. If Kepler 62e possesses a thick atmosphere, which its size and estimated gravity make plausible, it could maintain global temperatures that are warmer, more uniform, and less prone to dramatic fluctuations than those on Earth. This consistency could support lush conditions that remain hospitable for far longer than our planet has managed. A third exceptionally promising world is Kepler 1229b, an exoplanet orbiting a calm, older K-type star about 770 light-years away. Kepler 1229b sits squarely in the middle of its habitable zone and is estimated to be slightly larger than Earth, placing it in an ideal size range for atmospheric retention and climate stability. The planet is believed to receive a similar amount of stellar energy as Earth does, but with the added benefit of orbiting a star that evolves far more slowly, meaning the habitable conditions could last tens of billions of years. For life, that extended timeline is invaluable. Evolution on Earth took nearly 4 billion years to produce complex organisms, and a planet like Kepler 1229b could potentially offer a much longer, smoother path toward biological complexity. Finally, Kepler 452b, often nicknamed Earth's cousin, deserves a place on this list not because it is superhabitable by default, but because it sits at the edge of what might be possible for long-term habitability around the Sun-like star. Slightly larger and older than Earth, Kepler 452b has likely been in its star's habitable zone for billions of years. However, since it orbits a G-type star similar to our Sun, it may also be experiencing the early stages of the warming effect that Earth will eventually face. Its importance lies in the fact that it demonstrates how worlds around Sun-like stars may still achieve long-term stability, just not as effortlessly as their counterparts around K-type stars. While not the strongest candidate on the list, it offers valuable insight into both the limits and the possibilities of Earth analogs. Each of these planets exemplifies a different aspect of superhabitability: extended longevity, stable climates, favorable sizes, or warm, water-rich environments. Together, they highlight the diversity of worlds that could potentially surpass Earth in their ability to nurture life. And understanding what makes these targets compelling naturally leads to the next question: why slightly larger planets with stronger gravity could further enhance the potential for thriving, complex biospheres. One of the most intriguing insights to emerge from the study of superhabitability is the idea that a planet slightly larger than Earth, with moderately stronger gravity, might actually be a more fertile home for life. Size and gravity influence nearly every aspect of planetary habitability, and when they fall within an optimal range, they can create conditions that are more stable, more protective, and biologically richer than what Earth currently offers. A planet between about 1.2 and 1.5 times Earth's mass is often considered ideal, big enough to enhance habitability, but not so massive that it becomes a gas-shrouded super-Earth with crushing atmospheric pressure. This sweet spot in planetary size opens the door to thicker, longer-lasting atmospheres, more geological activity, and expanded areas of surface suitable for complex ecosystems. Stronger gravity helps a planet retain its atmosphere over billions of years, preventing the gradual loss of gases to space that can slowly erode habitability. Earth itself loses atmospheric particles constantly, and only its magnetosphere keeps this escape in check. A slightly larger planet with more gravity can keep its air dense and stable even if its magnetosphere is not as strong. A thicker atmosphere, in turn, distributes heat more evenly across the planet, reducing extreme temperature swings between day and night, or between polar and equatorial regions. This kind of climate stability creates a more uniform environment, one where life can take root in more places, not just along narrow belts of favorable temperature. The added atmospheric mass also provides better shielding from harmful cosmic and stellar radiation, giving surface life additional protection and potentially allowing biology to flourish in ways not possible on more exposed planets like Mars. Gravity also affects a planet's geological vitality. Slightly larger planets are more likely to maintain tectonic activity for longer periods, because their internal heat dissipates more slowly due to their increased volume. Plate tectonics play a crucial role in recycling carbon, regulating atmospheric gases, creating continents, and shaping diverse environments. On Earth, tectonic processes are believed to have been essential for stabilizing the climate over long timescales. A superhabitable planet with somewhat stronger tectonic activity could support a broader array of terrains, mountain ranges, coastlines, islands, and volcanic regions, all of which stimulate biodiversity by creating countless ecological niches. More diverse terrain typically leads to more diverse biology. Planet size also influences surface water distribution. A slightly larger world is more likely to have moderate oceans and abundant shallow seas rather than the extremely deep basins that dominate Earth. Shallow seas allow more sunlight to penetrate the ocean floor, expanding the areas where photosynthetic life can thrive. These nutrient-rich waters can serve as vast biological engines, producing more oxygen, supporting more species, and fueling a global ecology that is richer than anything Earth's deep oceans can sustain. Greater gravity also helps prevent water loss to evaporation over geological time, ensuring that oceans remain stable and persistent. All of these factors, atmospheric retention, heat balance, geological longevity, and water stability, add up to a profound conclusion. A slightly larger planet could be inherently more life-friendly than Earth, supporting ecosystems that are not only more resilient, but also more abundant and diverse. And with the advantages provided by enhanced size and gravity, we can now turn our attention to the kinds of surface conditions that would likely emerge on such worlds, and why those landscapes might be even more conducive to life than the environments we know here. When scientists imagine the landscapes of a superhabitable world, they envision surface conditions that go far beyond the familiar patterns of Earth. Conditions that maximize biodiversity, ecological stability, and the long-term flourishing of life. One of the strongest indicators of a biologically rich planet is varied terrain, because diversity in landscapes often translates directly into diversity in life. On Earth, regions with high geological and environmental variation, such as archipelagos, continental shelves, mountain valleys, and tropical coastlines, tend to support the most abundant and complex ecosystems. A superhabitable planet would likely boast an even richer tapestry of environments. Gentle mountain ranges, shaped by long-lasting tectonics, could create countless microclimates, each offering different temperatures, humidity levels, and geological features. Broad plains could support vast forests or grasslands where evolution thrives through constant competition and adaptation. Island chains, especially those in warm, shallow waters, would become cradles of rapid speciation, much like the Galapagos Islands but on a far grander scale. The more diverse the terrain, the more opportunities life has to specialize, explore evolutionary paths, and fill every available niche. Shallow oceans play an equally essential role in enhancing planetary habitability. Unlike Earth's deep, nutrient-scarce ocean basins, shallow seas allow sunlight to penetrate much farther, stimulating photosynthesis across large areas of the seafloor and powering immense food webs. These waters tend to be warmer and more nutrient-rich, promoting marine biodiversity at levels potentially far beyond what Earth's oceans currently support. On a superhabitable world, it's likely that shallow seas and sprawling coastal regions dominate the surface, offering ideal habitats for early life to emerge and for complex organisms to evolve. These environments encourage rapid evolutionary growth and energy-rich ecosystems that can sustain large populations. Coastlines, which on Earth are some of the most productive habitats, would be more widespread, creating vast zones where land and water interact in dynamic, life-supporting ways. This configuration allows life to flourish both on land and in the sea, creating a planetary biosphere that is interconnected and robust. Climate stability is perhaps the most critical factor tying all these surface conditions together. Earth's climate, while habitable, has been anything but stable. Ice ages, global greenhouse phases, and sudden cooling or warming events have repeatedly reshaped ecosystems and wiped out entire branches of life. A superhabitable planet, however, would likely maintain a far more steady climate, one without extreme ice ages or abrupt temperature swings. A thicker atmosphere, moderated temperatures, and balanced geological processes would allow warm, humid conditions to persist across much of the planet. This kind of stability fosters dense forests, expansive wetlands, rich grasslands, and thriving coral-like marine systems that could run uninterrupted for billions of years. Such consistency also encourages the accumulation of biomass, meaning the planet could support far larger quantities of plant and animal life. A stable climate ensures that rainfall patterns are reliable, nutrient cycles remain unbroken, and ecosystems don't experience the severe collapses that Earth periodically faces. On a superhabitable world, the combination of gentle seasonal shifts, moderate global temperatures, and even distribution of heat would enable life to exist in abundance across nearly the entire planet, not just in isolated pockets of favorable conditions. These enhanced surface environments, diverse terrains, shallow oceans, and long-term climate stability work together to create a world where life thrives more easily, spreads more widely, and evolves more deeply than it does on Earth. And once we understand how the surface supports life on these worlds, the next step is to examine the skies above them, because the atmospheric composition of a planet may be the ultimate ingredient that determines whether life can truly flourish. A planet's atmosphere acts as the gateway to its habitability, shaping temperature, shielding the surface from radiation, and providing the raw materials life needs to grow. On a superhabitable world, scientists expect the atmosphere to be thicker, richer, and more stable than Earth's, offering a level of environmental protection and biological support that surpasses what our planet currently provides. Such an atmosphere would likely contain a balance of gases that promote life's biochemical processes while maintaining a warm, steady climate. For instance, slightly higher concentrations of carbon dioxide than Earth's, still well below levels that would trigger runaway greenhouse conditions, could enhance plant growth and drive robust carbon cycles. Combined with a thicker blanket of nitrogen and trace gases, this composition could create a gentle greenhouse effect that keeps temperatures comfortably warm across the planet, even in higher latitudes. The additional atmospheric density would also help distribute heat more evenly, reducing harsh climate contrasts and minimizing the risk of frozen or barren regions. Oxygen levels on a superhabitable world might also be higher, depending on the age and maturity of its biosphere. On Earth, high oxygen concentrations have enabled the evolution of large active animals and complex ecosystems, but our oxygen levels are ultimately tied to the stability and productivity of our biosphere. A more ancient or more efficient biosphere on a superhabitable planet could generate even higher oxygen levels, promoting richer ecosystems and possibly enabling forms of life with greater metabolic intensity than anything found on Earth. The thicker atmosphere would also provide superior protection from cosmic rays and ultraviolet radiation, creating a safer environment across the surface where organisms could thrive without the constant threat of genetic damage from radiation exposure. Another hallmark of a superhabitable atmosphere would be its long-term stability. Earth's atmosphere has undergone dramatic shifts in composition, sometimes causing catastrophic climate consequences. A thicker, more stable atmosphere, combined with the steady energy output of a long-lived K-type star, would create a self-regulating system that keeps temperatures and gas concentrations within life-friendly ranges over billions of years. This stability reduces the risk of mass extinctions caused by sudden climate change and allows evolution to proceed uninterrupted, building deeper and older lineages of organisms. Detecting such atmospheres from across the galaxy requires sophisticated tools and methods, and this is where modern astronomy has made tremendous strides. Scientists use a technique called transit spectroscopy, which involves studying starlight that passes through a planet's atmosphere when the planet crosses in front of its star. As the light filters through, molecules in the atmosphere absorb specific wavelengths, imprinting a chemical fingerprint onto the starlight. Telescopes like Hubble and the James Webb Telescope analyze these patterns to determine which gases are present. Molecules such as water vapor, methane, carbon dioxide, oxygen, and ozone are of particular interest because their presence can reveal clues about a planet's climate and potential biosphere. Another method involves direct imaging, where telescopes block out starlight to capture the faint glow of a planet itself. This glow often carries spectral information that can reveal atmospheric composition. Future telescopes will push this capability much further, enabling astronomers to identify the signature of biosphere-friendly gases with unprecedented precision. Additionally, measurements of a planet's heat distribution using infrared observations can help scientists infer atmospheric thickness and climate behavior. Together, these detection methods allow astronomers to build a detailed picture of exoplanet atmospheres, even from immense distances. As we analyze more worlds and identify those with thick, stable, life-supporting air, we move closer to answering the next crucial question. If such atmospheres exist, what signs of life might they contain that we can detect across the light years? When astronomers search for life on distant worlds, they're not looking for cities, forests, or alien creatures. They're looking for biosignatures, the chemical footprints that life leaves behind in a planet's atmosphere or on its surface. These signatures are the most realistic clues we can detect across interstellar distances. And on a superhabitable planet where life may be more abundant, more diverse, and more active than on Earth, the signals could be even stronger. The most sought-after biosignatures are gases that are difficult to produce in large quantities without biological processes. For instance, oxygen is one of the clearest indicators of life, because it's highly reactive and quickly disappears unless something, like photosynthesis, is constantly replenishing it. A planet with high levels of atmospheric oxygen may host vast forests, thick microbial mats, or abundant marine plant life sustaining a powerful oxygen cycle. Another key biosignature is methane, especially when found alongside oxygen. On Earth, these two gases coexist because living organisms continuously maintain them. Without life, methane breaks down quickly and oxygen reacts with it until both are balanced out. Detecting both gases at the same time in significant amounts points strongly towards biological activity, because such a combination is thermodynamically unstable without constant replenishment. Similarly, ozone, a byproduct of oxygen chemistry, can indicate the presence of a breathable atmosphere and indirectly the biological processes that generate oxygen in the first place. Scientists also look for nitrous oxide, N2O, which on Earth is most commonly produced by microorganisms. While trickier to detect, high levels of N2O could signal a thriving biosphere filled with active metabolic cycles. Beyond individual gases, researchers look for disequilibrium patterns, chemical combinations that shouldn't exist together unless life is influencing the system. For example, the simultaneous presence of carbon dioxide, methane, and oxygen in specific ratios suggests a dynamic and continuous set of biological reactions. These patterns are far more persuasive than any single gas alone because they reflect the complex balance that only a living ecosystem can sustain. Scientists also consider the possibility of more exotic biosignatures, gases like dimethyl sulfide, isoprene, or even certain chlorine-based compounds that, on Earth, are almost entirely produced by biological processes. While these are harder to detect with current instruments, they may become key indicators as telescope technology advances. Scientists also pay close attention to surface biosignatures. The reflective properties of a planet, called its spectral albedo, can reveal unusual patterns, such as the red edge phenomenon seen on Earth, where vegetation reflects infrared light in a very specific way. If a planet's surface shows an unexpected reflective spike consistent with photosynthetic organisms, that could be a powerful sign of widespread plant-like life. Even the presence of pigments, microbial mats, or large-scale biological structures could, in principle, be detectable by high-resolution future telescopes. Scientists are especially interested in spectral features that repeat seasonally, which could indicate growth and decay cycles similar to Earth's vegetation patterns. As our instruments become more precise, we may soon be able to identify combinations of gases and surface signatures that unmistakably point toward biological processes. On a superhabitable planet, where conditions favor abundant life, these signals might be even stronger, clearer, and more diverse than anything detectable from Earth-like worlds. And as we refine what biosignatures reveal, the next critical question becomes how we detect these planets in the first place, through the telescopes and techniques that allow us to see across the gulf of space. Detecting and studying potential superhabitable planets requires a combination of sophisticated techniques and powerful telescopes capable of gathering faint signals from worlds orbiting stars many light years away. The process begins with one of the most foundational tools in exoplanet science, the transit method. Telescopes like Kepler and TESS watch thousands of stars at once, measuring tiny dips in brightness that occur when a planet passes, or transits, in front of its star. From these subtle dimming events, scientists can determine a planet's size, orbital period, and approximate distance from its star. This initial data is crucial for identifying planets that reside in the habitable zone, where temperatures might allow liquid water to exist. While the transit method doesn't reveal everything, it serves as a starting point for narrowing down thousands of worlds to a smaller list of potentially superhabitable candidates. Once a promising world is identified, astronomers turn to transit spectroscopy, a technique that analyzes the starlight filtering through a planet's atmosphere during a transit. Different atmospheric molecules absorb different wavelengths of light, leaving behind patterns, chemical fingerprints, that telescopes can read. Instruments like the Hubble Space Telescope and, more recently, the James Webb Space Telescope have the sensitivity needed to detect gases such as water vapor, methane, carbon dioxide, and potentially even oxygen. By comparing these absorption features across multiple transits, scientists can build remarkably detailed profiles of atmospheric composition. On superhabitable candidates with thick, stable atmospheres, these signatures may be easier to detect, offering clearer insights into their habitability. Another key technique is radial velocity measurement, used by ground-based observatories such as HARPS, Espresso, and the Planet Finder spectrograph. When a planet orbits a star, it exerts a small gravitational pull that makes the star wobble back and forth. This wobble shifts the star's spectral line slightly toward red or blue wavelength. By measuring these shifts, astronomers can determine the planet's mass, information that, combined with its size from transit data, reveals its density. Density helps distinguish between rocky superhabitable planets and gas-dominated mini-Neptunes that lack solid surfaces. High-precision radial velocity instruments are critical for confirming whether a candidate planet falls within the mass range that supports habitability and long-term atmospheric retention. As technology advances, another method, direct imaging, is becoming increasingly important. This technique involves blocking the overwhelming glare of the host star to capture the faint light reflected or emitted by the planet itself. While currently limited to larger, younger planets far from their stars, direct imaging will soon allow astronomers to study terrestrial-sized worlds more closely. The upcoming Nancy Grace Roman Space Telescope, for example, is designed with an advanced coronagraph that will push the boundaries of direct imaging, potentially allowing us to photograph planets similar in scale to Earth and detect signs of atmospheric scattering, clouds, and even surface features. With these tools, astronomers will gain the precision needed to not only find these worlds, but to understand them deeply enough to judge their true potential for life. All of these detection methods, transit, spectroscopy, radial velocity, direct imaging, and the capabilities of future telescopes work together to sharpen our view of distant exoplanets. As we refine our ability to find and study worlds that may surpass Earth in habitability, we confront a new challenge. Many of the most promising candidates lie incredibly far away, far beyond our reach for now. Understanding why these worlds are so distant and why that distance complicates our exploration brings us to the next stage of this cosmic journey. One of the most striking realities about the search for superhabitable planets is that many of the most promising candidates lie astonishingly far from us, often dozens, hundreds, or even thousands of light years away. This isn't because closer superhabitable worlds don't exist, rather it's largely a consequence of how and where our telescopes have been searching. The earliest large-scale exoplanet missions, such as the Kepler Space Telescope, focused on small patches of the sky instead of surveying nearby stars. Kepler stared at a single region in the constellation Cygnus for years, scanning over 150,000 distant stars all at once to catch the faintest possible planetary transits. This strategy allowed us to discover thousands of exoplanets, but because the stars were so far away, nearly all of Kepler's most compelling finds, including planets like Kepler 442b and Kepler 62e, sit at distances of hundreds or even thousands of light years away. These planets captured our attention not because they are nearby, but because they happen to be among the stars Kepler observed with extraordinary precision. Another reason the most promising candidates appear far away is that our ability to detect small, Earth-sized planets improves when the stars are dim, simply because the relative brightness dip during a transit becomes easier to measure. K-type and N-type stars, the cooler, longer-lived stars most likely to host superhabitable planets, emit less light than Sun-like stars. This makes their planets easier to detect with the transit method, which depends on observing a star's light slightly dim when a planet passes in front of it. However, the nearest K-type stars are not as well represented in earlier surveys, meaning that the best candidates often emerge from distant data simply because those were the stars we were monitoring most closely. As our technology advances and we deliberately shift our focus to nearby stellar neighborhoods, the distribution of candidates will likely change dramatically. Distance also poses serious observational challenges. The farther away a planet is, the harder it becomes to measure its mass, atmosphere, temperature, and surface conditions. Light from distant stars are weaker, their spectral fingerprints are fainter, and the subtle features that hint at biosignatures become buried in noise. Even our most advanced telescopes struggle to tease out the atmospheric composition of a planet hundreds of light years away. The James Webb Space Telescope can detect atmospheric features on some of these distant worlds, but even JWST pushes against the limits of what's possible when the target is so faint and so remote. And this means that many of the planets we call superhabitable candidates today are still frustratingly uncertain, intriguing silhouettes rather than fully understood worlds, because distance prevents us from observing them at the detail required to confirm their true nature. And there's a fundamental cosmic reason for the distance problem. Life-friendly planets orbit stable, long-lived stars, and many of these stars are not the most common stars in our immediate neighborhood. The nearest stars to the Sun include several M-dwarfs, which are notorious for their violent flares and atmospheric-stripping energy outbursts. While a few quiet M-dwarfs exist, they're harder to find, and their habitable planets are challenging to detect because the planets orbit so close to the star that the signals are difficult to distinguish from stellar noise. K-type stars, which are the most promising hosts for superhabitability, are common in our galaxy, but not particularly common in the very local space around the Sun. This means that many of the nearest potentially superhabitable environments are simply not within our immediate cosmic backyard. The distance issue doesn't just hinder observation, it complicates our long-term ambitions. The idea of visiting or even colonizing these worlds becomes staggeringly difficult when the nearest promising candidates lie hundreds of light years away. Even traveling at a fraction of the speed of light, a journey to the most enticing superhabitable planets discovered so far would take tens of thousands of years. Their remoteness is a reminder of how vast, challenging, and isolating our universe truly is, and why the search for nearby habitable worlds remains one of the highest priorities for the next generation of exoplanet missions. But while distance sets daunting limits, it also fuels a powerful sense of motivation. NASA, ESA, and other international space agencies recognize that if humanity hopes to understand the potential for life beyond Earth, or someday reach such worlds, we must accelerate our search, refine our methods, and direct our instruments toward the stars most likely to shelter superhabitable planets. That is where the efforts of global space organizations come into play, shaping the next steps of our exploration. Space agencies around the world, most notably NASA in the United States, ESA in Europe, and a growing network of international partners, play a central role in shaping the search for highly habitable and superhabitable exoplanets. Their priorities are driven by a mix of scientific curiosity, technological advancement, and the long-term vision of understanding humanity's place in the universe. NASA's strategy places strong emphasis on finding Earth-sized planets in the habitable zones of nearby stars. But in recent years, the agency has begun shifting toward a broader framework that includes the possibility of worlds even more favorable to life than Earth. Missions like Kepler and TESS were designed to identify exoplanet candidates by monitoring brightness changes in thousands of stars. But follow-up efforts increasingly focus on characterizing the atmospheres and conditions of these planets, an essential step in determining whether any of them qualify as superhabitable. ESA also plays a major role, contributing missions specifically designed to analyze exoplanet atmospheres in fine detail. One of their flagship initiatives is the Ariel mission, set to launch in the 2030s, which will examine the atmospheres of hundreds of exoplanets to understand their chemical makeup, temperature profiles, and cloud coverage. Ariel's capabilities will help scientists distinguish between worlds that are simply Earth-sized and those that possess thick, stable atmospheres consistent with long-term habitability. ESA's Plato mission, targeting an earlier launch, is designed to search for terrestrial planets around bright, sun-like, and K-type stars, precisely the stellar environments where superhabitable worlds are most likely to be found. Plato's high-precision measurements will contribute not just to detecting planets, but also to determining stellar ages, an essential metric since older, more stable planets tend to be stronger candidates for superhabitability. NASA's focus now includes developing technologies that can directly observe exoplanets, moving beyond indirect detection techniques. The upcoming Nancy Grace Roman Space Telescope, with its advanced coronagraph, will be one of the first tools capable of imaging rocky planets directly, potentially revealing atmospheric scattering and surface signatures. Beyond Roman, NASA is planning the Habitable Worlds Observatory, HWO, a next-generation mission explicitly designed to identify truly Earth-like and super-Earth-like worlds around nearby stars. HWO aims to detect biosignatures through direct imaging and advanced spectroscopy, marking a major leap forward in our ability to evaluate habitability. Its design is heavily influenced by the recognition that superhabitable planets, especially those around stable K-type stars, may be the most promising places to look for life. Other space agencies are entering the field. The Canadian Space Agency, CSA, collaborates extensively on exoplanet instruments, including contributions to JWST that have already produced some of the most detailed exoplanet atmospheric measurements in history. The Japanese Aerospace Exploration Agency, JAXA, is exploring missions aimed at studying star-planet interactions, critical for understanding how atmospheres evolve. Meanwhile, private organizations and international consortiums are funneling resources into large ground-based observatories like the ELT, GMT, and TMT, massive telescopes that will be capable of detecting planetary atmospheres and even possible biosignatures from Earth's surface. Collectively, these agencies are prioritizing a future where the detection of a truly superhabitable planet becomes not just possible, but expected. Their missions are designed with layered approaches, first identifying planets, then characterizing their atmospheres, then searching for chemical fingerprints of life, and eventually capturing direct images that reveal these worlds in unprecedented detail. This coordinated global effort reflects a profound shift in scientific ambition. Rather than simply cataloging planets, the goal is to find those that could rival or exceed Earth in their capacity to sustain life. And once the institutional groundwork is laid, scientists can begin exploring even more profound idea that superhabitability does not only imply conditions suitable for biology, but also worlds where evolution might advance further and more smoothly than it has here. When we talk about habitability, the conversation often centers on whether a planet can host life at all. But superhabitability pushes us to think much bigger, asking what conditions allow life not just to exist, but to flourish, diversify, and persist with fewer catastrophic interruptions. On Earth, evolution has been repeatedly disrupted by mass extinctions, 5 major ones and many smaller events, each reshaping the biological landscape, erasing entire lineages, and forcing life to start over from evolutionary ground zero. A superhabitable planet, however, might enjoy conditions so stable and forgiving that these evolutionary resets rarely, if ever, occur. With a thicker atmosphere buffering temperature swings, a gentle climate without extreme ice ages, and a calm host star that doesn't bombard the planet with lethal radiation bursts, life could evolve in a smoother, more continuous trajectory. This means species could develop greater complexity over longer periods, and ecosystems could accumulate biodiversity far exceeding anything Earth has produced. The value of fewer extinctions becomes clear when we consider Earth's evolutionary timeline. Complex multicellular life appeared roughly 600 million years ago, but much of that diversity has been wiped out multiple times, each extinction erasing millions of years of progress. Imagine a world where those catastrophic bottlenecks never happened, where life had billions of uninterrupted years to evolve without sudden climate collapses, asteroid impacts, or global volcanic eruptions. The result might be ecosystems richer in species, more intricate in structure, and far more stable than Earth's. Evolution could follow deeper and more varied paths, perhaps leading to biological innovations or levels of intelligence that never emerged here simply because life on Earth kept getting kicked backward. A superhabitable planet, therefore, isn't just a world where life can emerge, it's a world where life can reach its fullest potential. Climate stability also plays a critical role in shaping the ecological richness of a planet. Earth climate is driven by delicate feedback loops involving greenhouse gases, ocean circulation, volcanic activity, and solar energy.
These loops have tipped into instability many times, producing global glaciations, snowball Earth scenarios, and hothouse phases that squeeze life into narrow refuges. A superhabitable planet, with its thicker atmosphere and more even distribution of heat, could avoid such extremes altogether. Instead of oscillating violently between warm and cold periods, it might maintain a consistently mild, humid climate ideal for vegetation and marine productivity. This stable climate would create vast, uninterrupted forests, sprawling wetlands, and oceans teeming with life on a planetary scale. Every corner of the world, poles included, could support biologically rich environments instead of harsh frozen deserts. Another layer of superhabitability involves the window of evolutionary opportunity, or how long conditions remain favorable for life's development. On Earth, the sun's increasing brightness means our habitable window is limited. Despite Earth being approximately 4.5 billion years old, it has only a few billion years left before rising solar luminosity destabilizes our climate. By contrast, planets around long-lived K-type stars could enjoy stable, temperate conditions for tens of billions of years, giving life up to 5 times longer to evolve. This extended window allows evolution to explore complexity at a leisurely pace, producing organisms that refine themselves over monumental spans of time without being rushed by environmental collapse. The result could be ecosystems that are incredibly ancient, deeply interconnected, and biologically efficient in ways we've never observed. Superhabitability, then, is not only about chemistry and atmosphere, it's about time, continuity, and the absence of catastrophic interruptions. It's the idea that the universe may contain planets where conditions remain favorable not for millions, but for billions upon billions of uninterrupted years. On such planets, evolution would not merely struggle forward, it would thrive, innovate, and cascade into forms of life that could surpass the diversity and resilience of any biosphere Earth has ever known. And once we appreciate how deeply such worlds could shape the destiny of life, we can begin to imagine what kinds of organisms might arise under these ideal conditions. Creatures potentially more advanced, more adapted, and more varied than any that have ever walked our own planet. On a superhabitable world, one with stable climates, warm temperatures, shallow, nutrient-rich seas, and billions of years of uninterrupted evolutionary time, life could develop in ways that stretch far beyond what we see on Earth, yet still remain grounded in biological principles we understand. Evolution always shapes organisms according to their environments, and on a planet where nearly every region is biologically productive, life would likely become more diverse, more specialized, and more complex. In lush, evenly warm climates, plants can grow taller, broader, and more widespread, forming global forests where growth is not limited by droughts, freezing winters, or nutrient scarcity. With stronger gravity on slightly larger planets, vegetation might develop thicker trunks and deeper root networks to support their own weight, resulting in forests composed of colossal, sturdy plant analogs that stabilize ecosystems and pump vast amounts of oxygen into the air. These forests could host layers of life more intricate than any rainforest on Earth, multiple vertical strata filled with creatures adapted to every niche of light, humidity, and elevation. In the planet's expansive shallow seas, prime environments for photosynthesis, marine life could evolve into extraordinarily complex forms. The abundance of sunlight reaching the sea floor would create vast underwater meadows, coral-like structures, and microbial mats that form the foundation of massive food webs. With ample oxygen, aquatic animals could grow larger and more energetic than most Earth species. Some might develop elaborate bioluminescent signals for communication or hunting, while others could evolve advanced collective behaviors, forming schools or swarms with near hive-level coordination. Evolution in such a stable environment might favor organisms with complex nervous systems, capable of processing rich sensory information, especially in clear, shallow waters where visibility is high. These creatures might perceive ultraviolet or infrared wavelengths, giving them visual capabilities surpassing terrestrial animals. On land, animals could adapt to the slightly higher gravity by becoming more compact and muscular, developing strong skeletons and efficient circulatory systems to move against increased weight. Flight might still evolve, but flying creatures could have broader wings, more powerful muscles, and perhaps multiple sets of wings to compensate for gravitational forces. With stable, warm climates and constant biological productivity, life wouldn't need to hibernate, migrate, or endure seasonal die-offs. As a result, terrestrial organisms could spend more of their energy on growth and the evolution of intelligence. Some species might develop complex social structures, long lifespans, and cooperative behaviors that could rival or surpass those of Earth's most intelligent animals, dolphins, primates, and certain birds. Long evolutionary windows, potentially tens of billions of years, would allow intelligence to emerge repeatedly in different lineages. On Earth, intelligence evolved in only a few branches, but on a superhabitable planet with fewer extinction events and vastly more ecological niches, cognitive complexity could appear in multiple unrelated groups. Some intelligent species might be amphibious, capable of navigating both land and water with ease. Others might resemble Earth's cephalopods, but with even more refined problem-solving abilities made possible by stable marine environments that reward learning and adaptability. With a planet-wide abundance of resources and minimal environmental catastrophe, these intelligent beings could develop tools, cultures, and perhaps even early technologies at a pace shaped by curiosity rather than survival pressure. Microbial life might also diversify to extreme levels. On Earth, microbes dominate every ecosystem, but on a superhabitable world, microbial diversity could explode, with billions of distinct lineages evolving in separate niches, from thermal vents to expansive wetlands to floating aerial ecosystems sustained by thick, humid air. Specialized symbiosis between microbes and larger organisms could become far more advanced, shaping everything from digestion to communication to energy processing. Even life that doesn't resemble Earth organisms at all, yet still follows familiar biochemical rules, could emerge. Alternative pigments might dominate photosynthetic processes, producing forests of colors unlike anything seen here. Some life forms might rely on metabolic pathways that take advantage of atmospheric compositions slightly different from Earth's, leading to biologically efficient systems that outperform terrestrial metabolism. These organisms would not be alien in the unscientific sense, but would be logical evolutionary outcomes of a planet far more conducive to life than ours. Imagining these potential life forms isn't mere speculation. It is a natural extension of what we know about evolution, ecology, and planetary science. And once we envision life flourishing on such worlds, the question becomes irresistible. Could humans ever hope to reach and settle on a superhabitable planet, even if one existed close enough to dream of? Reaching and settling a superhabitable planet, even one far more hospitable than Earth, would require nothing short of humanity's most extraordinary leap, because distance remains the greatest barrier in interstellar colonization. Even if a superhabitable world were identified as a perfect candidate for human life, dozens or hundreds of light years away, getting there would demand technologies that challenge the limits of physics, biology, and engineering. The first step would be simply traveling to such a world, a journey that would take far longer than any human mission ever attempted. At current spacecraft speeds, even the nearest potentially habitable planets would take tens of thousands of years to reach. To make the journey feasible within human timescales, breakthrough propulsion technologies like nuclear fusion drives, antimatter engines, or laser-powered light sails would be necessary. These concepts are theoretically possible, but remain far beyond our current engineering capacity. Until such technologies are developed and tested, interstellar colonization remains an idea rooted in aspiration rather than logistical readiness.
But even if humanity managed to travel the enormous distance, the challenge of sustaining a human crew over such a long voyage is equally daunting. A multi-generational spaceship would be required unless faster-than-light concepts or cryogenic stasis become realities. A generation ship would need to function as a fully contained ecosystem, providing food, water, oxygen,
medical care, social structure, and psychological well-being for people who would never see Earth again and might die before reaching the destination. Maintaining such an ecosystem for centuries stretches far beyond any closed-loop life support system humans have ever built. Psychological resilience would become just as important as engineering reliability. Entire societies would be born, live, and die aboard the ship, carrying only cultural memories of the planet they left behind. The risk of mission drift, social instability, or system failures over centuries cannot be understated. Even the smallest error, like a decades-long decline in a critical nutrient or an unnoticed microbial imbalance, could threaten the entire mission. Assuming humans survived the voyage and arrived at a superhabitable world, the next challenge would be adapting to the planet's environment. Even if the planet's climate and atmosphere were more life-friendly than Earth's, differences in gravity, biochemistry, pathogens, and atmospheric composition could pose unexpected dangers. Slightly higher gravity, common on superhabitable worlds, might strain human cardiovascular systems and muscles, requiring extensive physical conditioning or even biomedical adaptation. Unknown microorganisms, while not necessarily harmful, could still trigger allergic or immune responses humans have never encountered before. The planet's ecosystem, no matter how inviting, would not have evolved with humans in mind. Its nutrients, toxins, and biological cycles could be benign or subtly incompatible with human physiology. Any colonization effort would require gradual settlement, significant environmental study, and likely some degree of terraforming or controlled habitat construction as humans adapt and learn how to safely live alongside native life. Cultural and social challenges would also shape the experience of colonization. A world far more fertile than Earth could support enormous population growth, but it would require careful planning to avoid repeating ecological mistakes made on Earth: overconsumption, habitat destruction, and species exploitation. Humans would need to approach this new biosphere with humility, recognizing that they are the newcomers in an ancient, interconnected system. Ethical questions about interacting with indigenous life, especially if it includes complex organisms, would demand unprecedented caution. Colonization would force humanity not only to adapt technologically, but also philosophically, redefining our role within a new planetary ecosystem. In the end, the potential for colonizing a superhabitable planet is both awe-inspiring and sobering. Such a world might represent a future refuge for humanity, or a second cradle of civilization. But reaching it would require solving problems that push every limit we know: propulsion, biology, psychology, sustainability, and ethics. And as soon as we consider the daunting challenge of making such a journey, we inevitably confront the technological barriers that stand between us and the stars, barriers that remain among the most formidable obstacles in all of science. The journey to distant superhabitable worlds is not limited by imagination. Humanity can dream as boldly as it wishes, but by physics, engineering, and the monumental gaps that currently stand between our ambitions and the technological reality needed to cross interstellar distances. The first and most fundamental barrier is propulsion. Our fastest spacecraft to date, Voyager 1, New Horizons, and the Parker Solar Probe, travel at speeds that are impressive by human standards, but painfully slow on a cosmic scale. Even Voyager 1, traveling at over 38,000 miles per hour, would take more than 70,000 years to reach the nearest star. Reaching superhabitable planets, most of which lie tens to hundreds of light years away, would require propulsion systems that accelerate spacecraft to a significant fraction of the speed of light. Technologies like nuclear fusion drives, antimatter engines, beamed propulsion via massive Earth or Moon-based laser arrays, or the propulsion systems envisioned by breakthrough Starshot represent theoretical pathways, but none are currently feasible at the scale necessary to transport humans, equipment, and life support systems. Even if such propulsion systems were developed, sustaining a spacecraft's structural integrity at relativistic speeds presents another profound challenge. Colliding with even a tiny particle of dust at a meaningful fraction of the speed of light could be catastrophic, releasing explosive amounts of energy. Engineers must imagine spacecraft with advanced shielding, perhaps magnetic fields, debris-deflecting hulls, or self-healing materials to withstand continuous high-speed impacts.
These ideas are promising on paper, but remain untested. Beyond shielding, the energy requirements themselves pose near unimaginable demands. Accelerating a large vessel to even 10% the speed of light requires tremendous amounts of energy, far more than humanity currently produces in an entire year. Creating and storing that energy safely on a spacecraft would require engineering breakthroughs in fusion, energy capture, or matter-antimatter production that are far beyond today's capabilities. Life support is another colossal barrier. Long-duration missions, even those lasting a few decades, require closed-loop systems capable of recycling air, water, and nutrients with near-perfect efficiency. Current life support technology, like that used on the International Space Station, is only semi-reliable and still requires frequent resupply missions from Earth. A journey to a superhabitable world may take centuries or even millennia, demanding systems that operate flawlessly for multiple human generations without external assistance. A single failure in oxygen regeneration, crop cultivation, or waste recycling could doom the entire mission. Engineers must design habitats that mimic Earth's ecosystems with extraordinary stability, a task far more complex than creating machines. It may even require engineering artificial biospheres, complete with microbial networks, plants, animals, and synthetic ecological checks and balances. The psychological and social barriers are equally daunting. A multi-generational mission would require a stable, self-sustaining society confined to a finite space for centuries. Issues like cultural drift, conflict, governance, mental health, education, and purpose become just as critical as propulsion or life support. A ship society must remain unified, technologically competent, and committed to the mission across many generations, something no human community has ever had to attempt. Strategies might include advanced virtual environments, genetically diverse populations, AI-assisted governance systems, or even cryogenic stasis. But each of these comes with its own scientific uncertainties and ethical questions. Navigation and communication add additional hurdles. Traveling to a planet hundreds of light years away requires precise navigation through regions of space we know little about. Radiation fields, interstellar clouds, rogue objects, and gravitational anomalies all pose risks. Communication with Earth would lag by decades or centuries, meaning colonists must operate with complete autonomy. The spacecraft must also be capable of decelerating upon arrival, a step that often requires just as much energy as acceleration. Any miscalculation in timing or trajectory could result in overshooting the destination star system entirely. These technological barriers collectively paint a picture of a journey that, with today's tools, remains impossible. But history teaches us that the impossible often becomes inevitable given enough curiosity, time, and innovation. Just as sailing ships once opened the world's oceans and rockets opened the space beyond Earth, future propulsion systems and closed-loop habitats will likely open the path between stars. Until then, humanity must prepare methodically, developing the technologies, strategies, and understanding needed to someday reach these distant superhabitable worlds. And as our capabilities grow, so too does our ability to investigate these planets from afar, through the next generation of telescopes and missions that promise to reveal whether superhabitable worlds truly exist. Looking toward the future, a new wave of powerful telescopes and ambitious space missions is poised to revolutionize our understanding of potentially superhabitable worlds. These instruments represent a shift from merely detecting distant planets to probing their atmospheres, surface conditions, and even seasonal changes with unprecedented precision. One of the most influential upcoming missions is NASA's Habitable Worlds Observatory, HWO, a next-generation space telescope specifically designed to search for signs of life on Earth-sized planets around nearby stars. Unlike earlier telescopes that focused on broad surveys, HWO aims to directly image exoplanets and analyze their atmospheric chemistry in detail, looking for biosignatures such as oxygen, methane, or ozone, signals that could reveal whether a distant world is truly capable of supporting life or even surpasses Earth in habitability.
With advanced coronagraphs and possibly even starshade compatibility, HWO will be able to block out starlight with extraordinary effectiveness, allowing us to observe planets that previously remained invisible. Meanwhile, the European Space Agency's Plato mission, planetary transits and oscillations of stars, scheduled for launch in the coming years, will play a crucial role in identifying new terrestrial planets around Sun-like and K-type stars, focusing particularly on older, stable systems that match the superhabitability profile. Plato is unique in its ability to measure stellar ages with high accuracy, which helps determine whether a planet has had enough time to develop complex life. Complementing it is ESA's Ariel mission, dedicated entirely to studying exoplanet atmospheres. Ariel will observe hundreds of worlds across different sizes and temperatures, creating the first large-scale catalog of atmospheric compositions. This data will help scientists understand which atmospheric traits are most common among habitable planets and which worlds deserve closer examination as superhabitability candidates. Ground-based observatories are also entering a golden age. The Extremely Large Telescope, ELT, currently under construction in Chile, will be the largest optical infrared telescope ever built, featuring a 39-meter primary mirror. Its extraordinary resolution will allow astronomers to study exoplanet atmospheres from the ground, measuring carbon dioxide levels, water vapor signatures, and even cloud patterns. The Giant Magellan Telescope, GMT, and the 30-meter telescope, TMT, will contribute complementary capabilities, enabling detailed spectroscopic analysis of planets orbiting nearby K-type and M-type stars. These instruments will greatly improve our ability to detect faint chemical fingerprints that indicate whether an atmosphere is stable, oxygen-rich, or potentially shaped by biological processes. Another promising innovation is starshade technology, which may soon be tested in space. A starshade is a massive, flower-shaped screen deployed tens of thousands of kilometers away from a telescope. When aligned perfectly, it blocks all starlight entirely, allowing the telescope to capture the faint glow of orbiting planets without needing an internal coronagraph. If successful, starshades could dramatically increase our ability to directly image Earth-sized planets, even around the nearest K-type stars, giving us crisp, detailed observations of worlds that may be superhabitable. Additionally, improvements in infrared survey missions could help identify the thermal signatures of distant Earth-sized planets, allowing astronomers to measure heat distribution and estimate whether a planet has a thick, stable atmosphere. Missions like the proposed Origin Space Telescope aim to push the boundaries of infrared sensitivity, potentially revealing atmospheric gases such as ozone or molecular hydrogen at levels that today's telescopes could never detect. These future prospects don't just represent better data, they represent a monumental shift in how we search for life. Instead of relying on indirect, incomplete signals, humanity is heading into an era where we can examine planets almost as if they were in our own solar system. With each mission, each new telescope, and each technological breakthrough, we move closer to answering the central question that drives this entire journey. If superhabitable planets exist, what would their discovery mean for us? That question brings us to the final reflection, one that ties together science, philosophy, and the future of humanity. Discovering a truly superhabitable planet, one that surpasses Earth in its capacity to nurture life, would be more than a scientific milestone. It would be a profound turning point in how humanity understands itself and its place in the cosmos. For centuries, Earth has been our reference point for what a living world looks like, the only example we have ever known. Yet the revelation that another planet may be older, richer, more stable, and more biologically fertile than ours would challenge the deeply held assumption that our world is somehow central or exceptional. It would force us to confront the possibility that life, far from being rare or fragile, is a natural outcome of cosmic processes, flourishing wherever conditions allow. And if the universe can produce worlds more hospitable than Earth, then life elsewhere might not only exist, it might thrive on a scale we have never imagined. The discovery of such a world would also reshape our aspirations and fears. Knowing that a planet exists where life could grow more abundantly,
evolve more intelligently, or persist far longer than on Earth, opens the door to a new kind of cosmic longing. It suggests a future where humanity might not be confined to a single vulnerable planet orbiting a star with a limited lifespan. Instead, we could imagine ourselves as part of a much larger story, one in which Earth is merely our birthplace, not our final home. That vision is both exhilarating and humbling, because it implies that the universe may already hold worlds where life has had billions of years of advantage over us, where civilizations, if they exist, might be older, wiser, and shaped by environments far gentler than our own. The search for superhabitable planets is therefore also a search for our cosmic peers, our possible ancestors, or even our distant successors. Philosophically, such a discovery would force us to rethink the scale of our significance. On a superhabitable world, evolution could produce ecosystems far more complex than Earth's. Dense forests spanning continents, oceans glittering with life, skies filled with species unimagined. Knowing that such beauty exists elsewhere in the universe would deepen our sense of awe, but it would also remind us of our responsibility to preserve the only biosphere we currently inhabit. Earth, despite its imperfections, is our home, and discovering a better world does not diminish its value. Instead, it encourages us to cherish what we have while inspiring us to strive for more, to explore, to learn, and to continue pushing the boundaries of human possibility. From a future-oriented perspective, the existence of a superhabitable world would give humanity a long-term horizon beyond anything we've ever contemplated. It would become a destination not for our generation or our children's, but for the distant future of our species, an anchor of hope that one day, even if Earth becomes uninhabitable, life could continue in a place that welcomes it even more generously. It would transform interstellar travel from a dream into a necessity, an ultimate chapter in humanity's long story. And even if reaching such a world lies far beyond our current technological reach, simply knowing it exists would shift our imagination, our science, and our collective purpose. In the end, the discovery of a truly superhabitable planet would remind us that the universe is not indifferent. It is fertile, dynamic, and filled with potential. It would show us that life is not a cosmic accident, but a recurring symphony wherever the right conditions align. And it would leave us with one unforgettable truth: that humanity is part of a vast living cosmos, with worlds out there waiting not just to be discovered, but perhaps one day to be called home. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.